In this video, we're going to be looking at kernels and one-to-one ring homomorphisms. So to get started, we're going to let phi be a ring homomorphism from R to S. And I'm going to start with the following question. If I know phi is one-to-one, what can we say about the kernel of phi? And I would actually encourage you to stop the video for just a few minutes, think about this question, and try to answer it for yourself. Hopefully you did stop the video and think about the question, and now what I want to do is look at the answer to this question. So let's look at the answer. Well, the first thing that I want to do is I want to recall that one-to-one means something very important. If we happen to have phi of A is equal to phi of B, then we know that A and B are exactly the same element in our domain ring R. And we can use this fact because we also know something else, and I want to recall another important fact. Any ring homomorphism takes the zero in the domain ring to the zero in the target ring. And so if we put these two facts together, we get the following thing. If phi of A is equal to the zero in S, and this would be if we start off with A belongs to the kernel of phi, then we have this equation is true, but that's going to imply that phi of A is equal to phi of the zero in R, and because phi is one-to-one, that will say A and the zero in R are the same thing, and I know that because phi is one-to-one. So if we put this together, we get the following important fact. If phi is a one-to-one ring homomorphism, then we know that the kernel of phi consists of only the zero element inside the domain ring 0 sub R. And that's a really important fact, and you should definitely get that written down. So what I now want to do is I want to turn my attention to the converse of that theorem. So we just proved the statement if phi goes from R to S is a one-to-one ring homomorphism, then the kernel of phi is nothing more than a singleton set consisting of the zero in ring R. Well, what I want to do now, as mathematicians often do, is I want to ask the question, is the converse of this statement true? And I would like you to stop the video again and take the time to write what the converse statement says for yourself, and then start the video. So hopefully you did that. The converse statement that we want to investigate says this. If the kernel of phi is nothing but the zero inside of ring R, then phi is a one-to-one ring homomorphism. And our question is this true? So what we're going to do is we're going to investigate that. And the way we're going to investigate that is we're going to set up the situation as follows. We're going to let phi be a ring homomorphism And all we know about this ring homomorphism is that we're going to be assuming that the kernel of this ring homomorphism is nothing except the zero element inside the ring R. And I want to think about what can we say about phi. In particular, is phi 1 to 1? Well, we can look at that by doing the standard way that we look at whether or not phi is 1 to 1. Let's assume that phi of A is equal to phi of B, where A and B are elements of R. Now, these two elements, they happen to be elements in the ring S, and because they're elements in the ring S, this is a ring equation, and I can subtract phi of B off both sides. So I know that phi of A minus phi of B is equal to the zero inside ring S. But that's enough to let me know that phi of A minus B is equal to the zero in S, and I know this because phi is a ring homomorphism. And that's where we use the fact that phi is a ring homomorphism. But let's look at what this statement actually says. This statement says that the element A minus B got mapped to the zero inside ring S. So that last statement is enough to say A minus B has to be inside the kernel of phi. But the kernel of phi consists of only one element, and that's the zero inside ring R. So that tells me that A minus B does have to be zero inside R, and that's enough to tell me that A and B are exactly the same element, which is then enough to tell me phi is a 1 to 1 ring homomorphism. And that's a super important fact. So what I want to do first of all is collect the two things that we've shown so far in this video and write them as a theorem. We have just gotten done proving the theorem that says this. If I have phi is a ring homomorphism, then what I know is the following thing. Phi is going to be 1 to 1 if and only if the kernel of phi is just the zero element inside of the ring R. And we just finished proving this. Now, there's some vocabulary that I want to talk about for just a bit, and I also want to talk about the significance of this theorem. The first thing is if the kernel of a ring homomorphism consists of nothing but the zero element, we say that the kernel of phi is trivial. Trivial meaning that it consists of just the zero element. And so what their theorem basically says is that phi is 1 to 1 if and only if the kernel of phi is trivial. That's how this statement is often done. The second thing that I want to do is I want to look at something else that's very important. This theorem up here gives us another way to show a ring homomorphism is 1 to 1. And I want to kind of get into that in just a little bit of detail. If we want to show that phi going from R to S is 1 to 1, we have two ways of doing it. One way that we can do it is we can use the definition of 1 to 1. In other words, we can prove if phi of A is equal to phi of B, then A has to be equal to B. Or alternatively, we can find the kernel of the homomorphism and show that that kernel consists of nothing but the 0 element. If we can do number 2, then we can assume that phi is indeed 1 to 1. So this will let us conclude that phi is 1 to 1. So it provides a different way of showing that homomorphisms are 1 to 1. And that completes this particular video.